Welcome back to Neural Intel. Sometimes the biggest breakthroughs come from questioning the things we take for granted. Today, we're diving into a paper from the Kimi team that does exactly that. They're looking at one of the most fundamental, baked-in pieces of every single LLM, the residual connection, and proposing a pretty radical upgrade called Attention Residuals. This could seriously rewire the backbone of these models, so let's dig in.
So here's the hook, and it's a good one. You know those standard residual connections? They're literally the backbone of every LLM out there. We just use them. They're part of the furniture. But what if that backbone, the thing we all rely on without a second thought, is actually a huge bottleneck? What if there's this critical flaw that's been hiding in plain sight this whole time?
Okay, so here's our game plan. First, we'll get into the weeds of the problem, which has a name, PreNorm dilution. Then we'll look at the elegant solution they came up with, Attention Residuals. And finally, we'll check out the payoff. And spoiler, it's a pretty sweet 1.25x compute advantage.
All right, let's jump right in. The problem with going deep, we all know residual connections are what let us build these ridiculously deep networks in the first place, right? But the core idea is just simple addition. Why on earth would that be a flaw?
Okay, so this is what we're all used to seeing. You've got your main information path, the residual stream. And each layer, doesn't matter if it's an attention block or an MLP block, does its thing, computes an output, and just dumps it right back onto that main path. It's like every layer is just shouting into the same crowded room, a total free-for-all.
And that chaos has a name, PreNorm dilution. Think about it. As you go deeper and deeper, that main highway just gets more and more jammed with information. The total signal, the magnitude of the hidden state, just keeps growing. So for a layer way down the line, say layer 100, to even be heard, it has to shout louder than everyone else. It has to produce a huge output. And what does that lead to? Yep, exploding gradients and a ton of training instability. The poor early layers get totally drowned out unless they scream right from the start.
So for us developers, this creates some serious headaches. First off, there's no way to be selective. Every part of a layer gets the exact same jumbled up signal. Second, when information from an early layer gets buried, it's just gone. You can't get it back, which again forces those deeper layers to overcompensate, making everything unstable. The analogy the paper uses is spot on. It really is like a giant game of telephone, where the original message gets more and more mangled with every layer.
Okay, so if just adding everything together is the problem, what's the fix? Well, this is where things get really clever. The authors had this big idea. Everyone knows attention is amazing for looking at a sequence of tokens. But what if? What if we apply that exact same powerful idea to the network itself? What if we could attend over the sequence of layers?
And this quote from the paper just nails it. They're basically saying, hey, remember RNNs? Remember how they had that terrible bottleneck where they tried to cram the entire history of a sentence into one little hidden state? Attention blew that wide open by letting the model look back at any token it wanted. The proposal here is to do the exact same thing, but for the depth of the network. It's a fantastic parallel.
And here's what that looks like. This is full AttnRes. Instead of just blindly adding its output to the pile, each layer now gets to be smart. It learns its own little query, and it uses that query to look back at the outputs of all the previous layers and say, I need a little bit from layer 3, a dash from layer 27, and I'll ignore the rest. It selectively pulls exactly what it needs. So that chaotic, jumbled highway, it's now a super efficient, targeted information retrieval system. Way better!
Okay, but if you're like me, your engineering senses are probably tingling right now. Wait a second. Attending over every single previous layer? That sounds ridiculously expensive. Can you imagine the memory footprint? The communication overhead in a big distributed training run? How in the world does that actually scale without grinding everything to a halt?
And yeah, that is absolutely the right question to be asking. And the good news is, the authors knew this was coming. They didn't just stop at the cool theory, they actually engineered a really practical solution to make this whole thing work in the real world.
And that solution is called block AttnRes. It's a really clever, pragmatic compromise. So instead of attending over every single layer, which is crazy expensive, you group them into blocks. Let's say 8 layers per block. Inside a block, it's just business as usual, standard residual connections. But when a layer needs to look outside its block, it doesn't look at all the individual layers. No, it just looks at the final compressed summary from each previous block. So instead of attending over, say, 120 different things, it only has to attend over maybe 16 block summaries, much more manageable. And this little chart just lays out the trade-off perfectly.
Full AttnRes has memory costs that scale with L, the number of layers. That's bad. Block AttnRes, the cost scales with N, the number of blocks, which is way, way smaller than L. That's good. This is the key that makes it a perfect fit for the kind of large-scale training we're all doing right now.
All right, time for our first neural signal check. Let's boil this down to what really matters on a technical level. That move from O of LT to O of ND memory and communication cost, that's not just an incremental improvement. That is the crucial engineering leap. It's what transforms attention residuals from a cool idea in a paper into a viable, practical drop-in replacement you could actually use in your training pipeline today. That's the real magic here.
And they didn't stop there. They also threw in some really slick system-level optimizations. For training, they use smart caching to stop GPUs from sending the same data back and forth in a pipeline parallel setup. For inference, they've got this two-phase strategy that smooths out memory costs. And the bottom line? All this extra power comes with less than a 4% overhead in training time and less than 2% in inference latency. That is just remarkably efficient.
Okay, so let's recap. We've got a clear problem, and we've got a super clever, production-ready solution. But now for the billion-dollar question, right? Is it actually worth it? Do all these engineering gymnastics actually give us better, faster models?
Well, the scaling laws pretty much tell the whole story. What we're looking at here is validation loss versus how much compute you throw at the problem. And it's clear as day. The AttnRes models consistently get to a lower loss for the same amount of compute. The paper actually crunched the numbers, and what it means is that AttnRes gets you the same performance as a standard model trained with 25% more compute. Let me say that again, a 1.25x compute advantage. In the world of LLMs, that is a massive, massive win.
And these two plots show us exactly why it's working so much better. On the left, you've got your standard baseline model. See how those output magnitudes just go nuts, growing bigger and bigger with each layer? That is PreNorm dilution right there on the screen, and the gradients are all over the place. Now look at the AttnRes model on the right. It's so much calmer. The outputs stay nice and controlled, and the gradient flow is way more uniform. It's just a fundamentally healthier, more stable way to train.
And that brings us to our second neural signal check. That nice, uniform gradient distribution we just saw? That's not just aesthetically pleasing. It's the whole technical ballgame. When your gradients are flowing that smoothly, it means every single layer in the network, from the very first to the very last, is actually learning and getting meaningful updates. This directly tackles those classic, painful, vanishing, and exploding gradient problems that have plagued super deep networks for years. It's a huge deal. So all that healthy training has to show up somewhere, right? And it does, right here on the downstream benchmarks. AttnRes beats the baseline pretty much everywhere, but check out where the really big jumps are. On GPQA Diamond, which is a beast of a reasoning benchmark, it gets a massive 7.5-point boost. Same story on Math and Human Eval, both up significantly. This is a huge clue. It tells us that getting this depth-wise information flow right isn't just a nice-to-have, it's probably critical for unlocking more powerful, complex reasoning. Okay, so let's pull all this together. What does this all mean for us, for the developers and engineers who are actually out there building these things?
I think there are 4 big takeaways here. 1, that standard residual connection we all use, it's a hidden performance killer. 2, this idea of applying attention over depth is a genuinely powerful new way of thinking about model architecture. 3, block AttnRes isn't some pie-in-the-sky research idea. It's an engineered, production-ready solution you can drop in right now with almost no overhead. And 4, the payoff is totally worth it. You get more stable training and a model that's way better at complex reasoning.
But you know, a really great paper always leaves you with more questions. They've absolutely nailed the case for pre-training. But what about everything that comes after? How does having this new superpower, this selective access to different depths, affect things like fine-tuning? Or what about model merging? Or techniques like LoRa? Does this change how those work? We don't know yet, and that's a super exciting area for new research.
And I'll leave you with this final, bigger picture thought. This paper took a part of the transformer architecture that we all thought was basically set in stone, the residual connection, and made it dynamic and intelligent using attention. So the question is, what's next? What other fixed part of the architecture is just sitting there, waiting for its own attention-based revolution? Something to think about. That's all for this breakdown on Neural Intel. Thanks for tuning in.